Detecting pipeline leaks on land and at sea. Our guest today uses special technology to locate leaks quickly before they become hazards. Offshore and onshore, how timely leak detection is critical for people and the environment. That's next on this episode of Technology Today. We live with technology, science, engineering, and the results of innovative research every day. Now, let's understand it better. You're listening to the Technology Today podcast, presented by Southwest Research Institute. Transcripts and photos for this episode and all episodes are available at podcast.swri.org. Hello and welcome to Technology Today. I'm Lisa Pena. Across the U.S., a vast network of pipelines carry oil and gas from the point of production to our communities. Sometimes weak spots develop or damage occurs to the system, causing leaks. That's when our SwRI experts and their cutting-edge technology are called in. SwRI Engineer Shane Siebenaler, director in our Fluids Engineering Department, joins us now to tell us about the methods used to detect leaks before they become problematic. Thanks for joining us, Shane.
Nice to be with you.
So let's start by understanding the big picture. What is the role of pipelines in our economy?
Sure. So we use petroleum in our everyday lives. We use our homes. If you have a plastic water bottle, it came from petroleum. Chances are, if you plug in your electric car, the power and electricity that's used to charge that car came from a power plant that is likely using fossil fuels. And so we need to move the petroleum from the point of its generation to the point of its use. And we can do that in different ways. You can put that on a truck, you can put that on a rail car. But pipelines offer a fairly efficient and safe mode of transporting the fluids from where they're generated to where they're used.
So what type of leaks are you looking for?
Right, so we can think of pipelines as either carrying liquids. So for example, gasoline, jet fuel, crude oil. Some pipelines carry natural gas. This is what you would use, for example, in your home, and that is primarily methane. And then there's also pipelines that carry substances like butane that are liquid while they're in the pipe, but if they were to leak out, it would vaporize and cause a gas leak. So we're looking for both liquid leaks and gas leaks.
All right. And what dangers do leaks pose, either gas or liquid, and why is it important to find them quickly?
So with the liquid leak, the primary concern is contamination of the environment. So you can imagine crude oil getting into a creek bed or onto some kind of environmentally sensitive area. That takes a while to clean up. It can also impact groundwater. With the gas leak, there's two concerns. One is that it can cause an explosion, so it can ignite fairly easily, which can cause damage to buildings and threaten the lives of people. It also can release methane, which is a very potent greenhouse gas. So large leaks can have impact on the climate.
And what are the first signs of a leak, either gas or liquid? What are you looking for?
So for one thing to point out is that traditionally many leaks are actually found by the public. They're not found by leak detection systems. So as a member of the public, for example, on a liquid leak, you might be able to see it if it's crude oil. You certainly would be able to smell it. So for example, there have been leaks of gasoline in the swamp areas where it was found by somebody smelling it. With a gas leak, you're unlikely to actually see a physical change unless there's a fire. The gas is colorless. From a pipeline operator perspective, there's instrumentation in the pipeline to measure things like pressure, temperature, flow rate, and a large enough leak will cause an anomaly that may be visible within that data. So a leak is typically going to be noticed by the pipeline company through the data that's coming in, whereas a member of the public will actually see or smell the hydrocarbon.
And when we're talking about liquid leaks, you're going to have different signs of leaks, whether you're out in the ocean or you're on land. It seems pretty obvious you'll see it in terms of a liquid leak, but can you talk a little bit about that?
So a liquid leak into the ocean, most oil that would come out of a well under the ocean is actually lighter than water and it floats. So think about if you were to put, cooking oil and water in a Pyrex container, that oil is going to float to the top. The same thing happens in the ocean. and you would see an oil slick or an oil sheen, and that can be detected by marine vessels. Oftentimes, it is detected by the air, helicopters or airplanes flying over. A liquid leak on an onshore pipeline has to get to the surface to be large enough to be able to see. So, some of the larger leaks in recent US history have actually been ones that persisted underground, including under snow cover for longer periods of time before they actually reached a surface where somebody could see them.
And what causes these leaks?
So for particularly for onshore pipelines, the two most common causes are corrosion. So this would be, think of it as rusting or eating away the pipe. And that can happen either from the outside. So for example, on older pipes that are not coated, water damage can essentially corrode the outside of the pipe. It can also happen from inside. And the other, the most common cause would be third-party damage. So somebody accidentally hitting the pipe. And that could be somebody not knowing that there's a pipeline there and they are digging, or oftentimes it's actually through contractors who are hired to do work near the pipe and inadvertently strike the pipe.
So, how often does this damage occur? How often do leaks happen? We see them on from time to time on the news, but is this a major problem?
Yes, so there are multiple reportable leaks every single day in the United States. And so these are leaks that trip a threshold that are reportable to the government. And in a normal year, even without a very catastrophic accident, the damage costs and cleanup costs are on the order of several $100 million per year in the United States. Now, one thing to note is that while these are kind of high profile events, it's very similar to air travel versus car travel. Far more people are killed driving cars than flying in airplanes, but it makes the news when an airplane crashes. And the same thing happens with pipeline spills. You are far less likely to have a spill on a pipeline than you are from a rail car or a truck. But when it happens, and particularly when it happens in a sensitive area, when it happens near people, or where it's a large leak, you notice it more. But as far as it being a big problem, there is significant environmental consequences as well as human safety.
So, you want to detect these leaks quickly. What is the next step, and what happens once a leak is detected?
So we typically need a human in the loop. So for example, even with a sophisticated leak detection system, an alarm would come in and a human needs to make an evaluation. Is it a legitimate alarm? Where is the leak? And then they would need to take action to stop it. So for example, shutting down the pipeline, um, dispatching a team to go and actually put their eyes on it and initiate the cleanup. An interesting shift in the past few years is that there used to be a tendency when an alarm came in is you had to actually prove that it was a real leak before you took action. Most pipeline operators today have the opposite effect. They assume that every alarm that comes in is legitimate, and they have a time in which the operator would have to prove otherwise. And so an example would be you might have a 10-minute window where an alarm comes in, and unless you can somehow determine that it was a false alarm within 10 minutes, you have to shut the pipe in.
Okay, so just so that we're clear and we understand how pipelines work offshore, we can picture onshore pipelines under the ground. How is the pipeline network set up offshore, under the sea?
So some pipelines sit on the sea floor. So imagine a pipe literally resting on the mud on the bottom of the sea floor. When the pipe comes into shallower waters, it oftentimes is buried. So it is very similar to an onshore pipeline. You want to avoid something hitting that pipe or it interfering with other activities. So oftentimes as it comes closer to shore, it will go into a buried mode.
So it's pretty similar onshore and offshore. You're dealing with the same type of pipeline infrastructure.
You're dealing with similar infrastructure. It is a different story in how you would access that pipe. So imagine you get a leak alarm in the middle of a rural area. You can send somebody out in a truck and they can go put their eyes on it. A offshore pipe, particularly in a deep water environment, is going to require that you send a submersible down. And typically, this would be an unmanned vehicle that is robotically controlled with cameras. And so the timing of that is very different than you would have in a response for an onshore.
All right, so we have exciting things happening at SwRI, a lot going on to detect these leaks. How are we advancing state of the art technology to detect leaks onshore and offshore?
So we both develop technology and help other companies in their technology development. And this is everything from lab scale, doing control tests, all the way out to implementation in the field. And so we need these systems, for example, to be able to work in the summer in South Texas, in the winter in North Dakota. And one element in recent years that the Southwest Research Institute has particularly been involved in is adding artificial intelligence and more specifically machine learning. So I mentioned earlier that you have a human in the loop to make a judgment as far as whether or not an alarm is real. So imagine a system with a lot of data coming in. You don't want to have somebody who has to stare at the screen all day and make real-time judgments of trends. So we are able to add a layer for a lot of autonomy to be done by the computer, and that allows for better decision making in a more concise manner for the operator.
Could you walk us through one of this process? You deploy the technology. Are we talking about a drone? Are we talking about what is the technology look like? And step by step, could you walk us through it? What is it doing?
Sure. So maybe we'll start with that. A leak detection system can be either stationary, so it's permanently installed, or it can be mobile, so take like a drone. And a permanently installed, this could be individual sensors, for example, that are installed at various points along the line. It could be something in the form of a cable, so a fiber optic cable or vapor sensing tube that is actually installed next to the pipe along its entire length. For a drone or even an ATV, like something you could put on a four-wheeler or a truck, those are sensors that you could deploy on demand to various points on the pipe. And so the deployment would involve some initial testing and development to ensure how these types of sensors work in an ideal environment, in a very controlled environment. And then one thing that you need to then do is do additional testing before deployment in the field to understand how something in a realistic environment will work. So as an example, you can put a infrared camera on a drone to look for methane leaks. Well, are there other things in your environment, like the exhaust from trucks nearby, other gases that are being emitted, for example, in combustion that could fool the system into thinking that you're having a leak? And those are items that you may or may not think of in a lab environment, but when you're out in the field, you can determine. And so it's a little bit of an iterative process. The technology would go out in the field, you would do additional testing, gather data that may result in refining and improving the system before it's fully operational.
And who are your clients? Are they only oil and gas companies? Does it go beyond that?
So it can be oil and gas companies. We do work directly with technology developers. We do work with individual sensor makers. So we may have a company that is developing not an entire system, but for example, like a camera that would aid and be part of a larger system. And we've also done work for third parties who have a vested interest. It can be, for example, an environmental NGO that may want to understand leak behavior of certain sites.
And how long does it take when you're talking about a fixed system? How long does it take to install something like that? I'm envisioning, miles and miles of pipeline. What's the process to get it out in the field and get it working?
So for a new pipeline, it would be installed when the pipeline is being installed, and the timeline there is driven by installing the pipe, not the leak detection system. In a retrofit case, so for example, if you have a pipeline that doesn't have a system and you want to put one on it, it depends on whether it's a fixed sensor. So for example, a system where you're going to place a sensor every few miles at things like pump stations, compressor stations, That may be a fairly quick deployment. Um, Plowing in a cable along, hundreds of miles of pipe can take months to do.
All right. I'd like to talk to you a little bit about your personal experience in doing this type of work. It sounds like you're, dealing with onshore and offshore scenarios. Tell us about any unexpected findings in your research. Do you have any?
So one of the most interesting things as a researcher is what actually happens when a leak occurs. So oftentimes we get very fixated on the sensors themselves. And so what kind of temperature gradient can they detect or acoustic response? And where we find a lot of interest is the behavior of leaks. So for example, a very small leak may not actually make it to the surface. It may follow a very contorted path. Its temperature profile would not be what you would expect. And a lot of the advances we've made at SwRI in the past few years have really been in understanding how leaks behave, and that allows us to better design and develop technology to detect those changes.
And what are some of the findings about leak behavior that have really stood out to you?
So, for example, sensor placement makes a significant difference. Imagine a large diameter pipe. And just for illustration, imagine a leak on the very top of the pipe at the 12 o'clock position. Where your sensor is at will have an impact on whether or not you can detect that leak. So imagine a cable, for example, installed at the 6 o'clock or bottom of the pipe. You could still detect it, but the pipe might shield some of the acoustics. On a temperature-based system, the further away your sensor is from the pipe, the more of a likelihood you have that the temperature of the fluid actually equalizes to the environmental temperature. And so we've been able to characterize things like temperature profiles, acoustic profiles, and also responses like ground movement. Does the ground heave during a leak?
So, all these characteristics, the temperature, the acoustics, um, as you just mentioned, ground movement, they are all important to detecting a leak. I guess if you could explain a little bit more about how leak behavior, connect the dots for us, how leak behavior informs leak detection.
So for a gas leak, you can directly detect the gas itself. So for example, you can do this with an infrared camera. There's different laser technologies, and you're physically detecting the gas itself. In a liquid leak, most leak detection sensors are actually not detecting the physical fluid. So they're not a hydrocarbon detector. They're detecting some physical change. So I always view a leak detection system as an event detector. So they're detecting, for example, a noise that shouldn't be there, or a all of a sudden a sharp temperature spike in an area where you're not expecting it. And so what we often have to do is leverage physical changes in the environment as a way of indirectly detecting the leak.
All right, thank you. So, what is it sounds like you have a lot of experience out in the field. What is the oddest thing you've experienced during your field work?
Sure. So we've done this work all over North America. We've been in northern Canada during blizzard conditions. We've been in West Texas during the summer. We've had to shelter in place during tornado season in Kansas. We've had multiple instances, believe it or not, with animals. And so we one time had a test where we used an abandoned barn as a control center, and nobody told the animals that it was abandoned. And so we had animals coming in to our test. We installed a bunch of equipment in a pasture in California one time that was unused. And a few weeks later, the rancher put his livestock on that pasture and trampled all of our equipment. So we've actually, as we've had these instances, we've started to think through those kind of scenarios. So, for example, we recently done some work on our campus where we dug large pits, and we actually put fencing around it to ensure that deer and other animals didn't fall in.
And we have a lot of deer out here on our campus, so that is probably a good test area to see if you can keep the animals away.
Yes.
So yeah, that it doesn't get any more real than that. You were out there experiencing the elements, and animals, weather, and random equipment coming through. So, did the pandemic cause any changes to your work out in the field? Have you felt any pandemic related effects to your work?
Yes, and particularly the first year of the pandemic, I mentioned earlier that in order to evaluate these systems and move them towards deployment, we do need to go out in the field and test them. And with all the travel restrictions early on in the pandemic, that greatly reduced it. Also, we're relying on people who actually work in the field to be available. So, for example, members of the pipeline companies themselves, and there were a lot of restrictions on even their staff traveling. So that certainly put a damper in the first part of the pandemic. Interestingly enough, though, in the same way that the pandemic has forced us to learn how to use Zoom and WebEx and Microsoft Teams, and people have a lot more capabilities with video, we've seen similar things in the way that we do our testing. So some of the work that we've done in the past that would require a number of people from different companies to all fly in. We sometimes can now do that with only a couple people coming in and doing some of that on video. We've even explored using things like the Microsoft Halo augmented reality headsets where we could actually have one person out there. We can pull manuals up on the headset, take video, and actually have one person do the work of several people. So while it certainly has posed challenges, I think this has also driven this kind of work into a realm where we can take advantage of opportunities.
Yeah, so it sounds like as in every industry, we've all had to make changes, and sounds like you guys were quick to do that. So, what is next in this type of work? You mentioned machine learning, you mentioned working with drones. Are there any secrets you can tell us about upcoming technology or things to look out for with leak detection?
So certainly a focus on offshore leak detection is something that will be more and more pressing in the future. So we think of, for example, production in the United States happening in places like West Texas, North Dakota, Pennsylvania. A surprising amount of petroleum products do come from offshore. So one in every 7 barrels of oil that's produced in the United States comes from offshore platforms. These platforms are going into deeper water, they're going further from offshore, and many of these are going to get moved to shore via pipelines. And so this presents new challenges. So, for example, deeper waters than typically we've seen in the past, and that will involve different types of technology that can reliably detect a leak. As I mentioned earlier, unlike an onshore leak where we do have the ability to send somebody out there and physically put their eyes on it, is a much more cumbersome problem offshore. Also, on an onshore pipe, when we shut production down, that typically just stops the flow of oil, which has only a direct economic impact. When we shut production down offshore, it actually can introduce additional safety challenges. So, for example, there's something called hydrate formation, which think of it as basically methane ice that can plug the line if it's not flowing. And so we want to be sure that we can very reliably detect these leaks in our offshore setting.
All right, this is an ongoing research project and new technology on the way. So this is interesting, important work. You're an engineer, but what path would you suggest for someone interested in this type of research?
So it encourages them to think broadly, and particularly as it relates to the types of sensors. So we're talking about pipelines here today, but the same kind of technology that we're using to detect leaks and detect people hitting a pipe, you can use that to detect stability on a dam. You can detect an anchor hitting a pipe underwater. You can look at things like the effect of mudslides on a pipe. You can even use it to monitor traffic. And so instead of thinking it from the application standpoint, pipeline leaks, pipeline integrity, we can think about the actual sensors and how those sensors could be leveraged for other situations.
All right, so many applications. And is that a standard engineering path? Do you just study sensors, or what's the field that is most likely to get you into this line of work?
So starting with solving one problem and then pivoting to use that technology on another one. So as an example, here at SwRI, we've developed some technology that uses machine learning along with infrared images to autonomously detect methane leaks. We've repurposed that same technology for things like air quality. So here in San Antonio, where we're located, we have a problem with ozone, which is a respiratory irritant. And we've been able to use some of the same technology that was originally designed to look for pipeline leaks to now go look for substances that contribute to ozone formation. And so the underlying technology is the same, but the application is very different.
All right, really cool stuff you're working on. So, what is our takeaway today? What would you like our listeners to remember about your work?
So even as we start to move towards a cleaner economy, we are still going to be surrounded by pipelines. Those pipelines in the future may have things like hydrogen or carbon dioxide in them instead of petroleum, but the need to detect those leaks in a timely manner, in a very reliable manner, is going to be important to the ongoing safety of those assets.
Okay, leak detection important now and will be important in the future. Your team is really swooping in with, development, test, and evaluation of leak detection systems. And as you mentioned, understanding the physics of leaks, whether that be temperature changes or ground movement. So, in a way, you're really saving the day and preventing disasters. That's great work. And thank you for guarding the pipeline network that keeps our lives moving. And thank you for being here today, Shane, to give us insight into your important work.
Thanks for the conversation.
And thank you to our listeners for learning along with us today. You can hear all of our Technology Today episodes and see photos and complete transcripts at podcast.swri.org. Remember to share our podcast and subscribe on your favorite podcast platform. Want to see what else we're up to? Connect with Southwest Research Institute on Facebook, Instagram, Twitter, LinkedIn, and YouTube. Check out the Technology Today magazine at technologytoday.swri.org. And now is a great time to become an SwRI problem solver. Visit our career page at swri.jobs. Ian McKinney and Brian Ortiz are the podcast audio engineers and editors. I am producer and host Lisa Pena. Thanks for listening.